All right. Perpendicularity of a line and a plane. Woo! Bring a little bit of perpendicular into our little plane action here. This is going to be exciting. I'll tell you what. All right, so we got our line plane perpendicularity definition here for you. It says a line is perpendicular to a plane if it is perpendicular to every one of the lines in the plane that passes through its foot. So what that's saying is, if I draw a line through B, or this way, all these going through B, if they are in the plane and they go through B, the foot of that line, it needs to be perpendicular to all those in order to be perpendicular to the plane. And the converse of that is if we already have that AB is perpendicular to the plane, or we can prove that AB is perpendicular to the plane, then we get perpendicular to all of the lines in the plane that go through that foot. Okay? Because definitions are reversible, right? It seems a bit excessive to have to say that AB is perpendicular to all those just to prove that it's perpendicular to the plane. Well, fortunately for us, there's a theorem that can help us prove it a little bit easier. So a little thought to ponder here. Say we've got ST is a line that's intersecting in our plane at T. RT lies on the plane M. If ST was perpendicular to RT, could you guarantee me that ST was also perpendicular to the plane? Meaning every line that runs through T is perpendicular to ST. Well, I like to think about things in terms of construction, like real life stuff. If I had a 2x4 attached to a 2x4 making a right angle, could I guarantee that thing will stay up straight when you set it on the ground? You might be able to get it to balance, but it could topple over, right? It could lean one side or the other. Just because it's a right angle here, yes, that'll make sure that this vertical piece does not fall this way or fall away from it, but it could topple the other way. Like ST right here, it's not going to go towards RT or away from RT, but it could fall the other direction, right? It could fall over. What if I were to add in a second line, in this case TD? So we have ST is perpendicular to RT, and ST is perpendicular to TD. And both TD and RT lie in plane M. Now, when I look at this, okay, ST can't go towards RT or away from RT. It can't go towards TD or away from TD. It can't go any other directions as well because it's just held vertically with these two lines, okay? So what we have here is actually called our basic theorem, all right? If a line that is passing through the foot of a plane is perpendicular to two lines in that plane, then it's perpendicular to the plane. Okay, we're going to write that down on the next slide here. So this time, we can actually prove that ST is perpendicular to M. All right, so here's our basic theorem. If a line is perpendicular to two distinct lines in a plane, must pass through its foot in order to do that. You can't be perpendicular if you're not intersecting it. Then it is perpendicular to the plane. So as we see here, ST is perpendicular to RT. There's our foot passing through. ST is perpendicular to DT, passing through the foot. So ST is perpendicular to plane M. So we could say with this theorem, ST is perpendicular to M. And remember, we're doing a fancy capital cursive-y, maybe a nice little curly Q. Plane M. I like that. That looks classy. That looks like it's fit for a king's scroll back in the medieval times. You know, it's a good M right there. All right. Very cool. Awesome. So I could say that with this theorem here in a proof. Okie dokie. Now, what would be so valuable to proving that ST is perpendicular to a plane? Maybe I'm trying to prove ST perpendicular to another line. Maybe there's another line going on that passes through T, and I want to prove it perpendicular to that. If I prove it perpendicular to the plane, I can prove it perpendicular to any other line in the plane that passes through its foot. So that's where the helpfulness of this theorem comes in. Because by the definition, we know that it'd be perpendicular to any line in the plane. Whew! All right, looks like we have some lovely confusing things that happened here. These were all supposed to be segment marks over A, B, B, C, A, B, and B, E. but it confused the computers. All right, my iPad got confused, or the software did. Anyway, it says that C, B, D, and E all lie on plane CBE. It says that AB is perpendicular to BC, AB is perpendicular to BE. I know that BC and BD are congruent, and I want to prove that CAB is congruent to DAB. Okay, so I want to prove a couple angles up top there. It's a little hard to notate them. Maybe I shouldn't even try. I'm just going to go ahead and not try. But it's our angles that are up here, okay? There's a couple angles up there that we want to prove congruent. Cool? All right. Now I've got that BC, which is this guy back here, and DB are congruent. I've got perpendicularity, but that perpendicularity involves this guy and then the one behind it, okay? But not the one that's ABD. Because what I'm kind of thinking here is that if I got triangle ABC and ABD congruent, triangle ABC congruent to triangle ABD, I could get my proof, CAB and DAB, right, from CPCTC. And if I had that ABD was a right angle, I could do that pretty quick with the reflexive property of AB, right? It's kind of like the last video that we did there. If I had AB congruent to itself, whoops, right? If we had that guy congruent to itself, I'd have a little SAS action going on for these two triangles. But I don't have ABD as a right angle, so what the heck? Well, I've got that AB is perpendicular to BC. I've got that AB is perpendicular to BE. Wouldn't that mean that it's perpendicular to plane CBE? And I'm going to label this as plane, how about we go with R? Right? That looks like a fancy R. I could probably get a little fancier with it. I'm going to go with the stick first, and then let's curly Q the R. There we go, plane R. I like that. Okay, that's very cursive-y. If you even wanted to put a little doohickey over here, that's perfect. Okay, extra cursive. All right. So it's perpendicular to that plane, right? Because it's perpendicular to two lines in the plane. Okay. Well, if I've got that, then I can prove that it's perpendicular to DB, and away we go. We got some right angles. This is lovely. I think we've got ourselves an excellent, excellent plan. Let's do this thing. We've got ourselves a little outline. Let's go for it. Okay. So I've got my given as usual. Okay. So I want to say that AB is perpendicular to R. Extra cursive. Okay. And our reason would be either the basic theorem, that's cool, or we could say line perpendicular to two lines. Oops. In plane, then perpendicular to plane. Okay. And obviously it has to go through the foot. They have to intersect it in order to be perpendicular. Duh. Okay. So now that I have a perpendicular to the plane, I can say that AB is perpendicular to DB. Line perpendicular to plane, then perpendicular to any any line
Could Allison and Sarah
in plane.
Alexis.
So now that we have them perpendicular, we can get some right angle action going. So I know that angle, let's see here, ABC and angle ABD are right angles. The reason why I'm picking those is because those are part of the two triangles that I want to prove congruent, because they have the two angles that I want to prove congruent using CPCTC. So that's definition perpendicular. Okay. Let's see here. I think I'm going to want to prove that those right angles are congruent because it's looking like I'm going to use side angle side, a little SAS action, to prove those two triangles that I have written down there, right? Okay, I'm running out of room, so I'm going to have to move this up. Hopefully everything, oh boy, it's not moving along with it. Let's see here, what can Mr. Allen do? I'm going to make this smaller. Hey, that kind of works. Okay, lovely. Alrighty. Now, I want to prove those angles congruent. So, for step 5 will be angle ABC congruent to angle ABD. And their reason would be all right angles congruent. And lastly, we've already talked about the reflexive part. AB is congruent to itself. By reflexive. And now I've got my triangles congruent. So we've got triangle. How about ABC? It's congruent to triangle. And what's going to line up with that? It'll be ABD. That was by SAS. And last but not least, I've got angle CAB congruent to angle DAB. That is by CPCTC. Yeah. Woo. Lovely. Alrighty, we got our last proof of the day here. Again, a lot of these proofs very similar to two-dimensional proofs because we're dealing with triangles and things like that. Just a few new things dealing with our three-dimensional theorems that we've got going on, generally with perpendicular to a plane and pulling off of that. So first up, it says that P, A, and B all lie on plane M. That's what that little E means right there. This little E means that they're like a part of that plane. Okay? So PA and B are on the plane. Lovely. I've got CP is perpendicular to the plane. I've got that BAC, angle BAC, which is this angle, and ABC, which is this angle, are congruent. And I want to prove that PAB and PBA are congruent. Okay, angle PAB and angle PBA need to be proved congruent. All right, awesome. So, first off, if I got perpendicular to a plane, I know I can prove that CP is perpendicular to PA and PB, right? I can get that, and that's pretty much all I can get from that piece of the puzzle. Okay, so I need to look ahead in this proof a bit. I want to prove that PAB, and I'm going to mark that in blue, PAB and PBA, those two angles are congruent. Well, in order to get those two angles congruent, I could also get PA and PB congruent and use if sides then angles, right? If I get that, that's an isosceles triangle down there on that plane, I could use if sides then angles to get those. So I've got a couple options of how I'm going to even get there. Well, if I want to get PA congruent to PB, if I prove those two triangles congruent, I've got a shot at getting, or I'm definitely going to get PA congruent to PB by CPCTC. So I think one of my first goals is to get triangle CPA congruent to triangle CPB. How wonderful. Okay, so let's see what information I have to work with right now. Well, we've got the whole perpendicular aspect, right? So those guys are right angles. Actually, let me change my color back. Let's work with what we know. So those guys are right angles there and there. Cool. Ooh, I've got that angle CAB and CBA congruent. Couldn't I use if angles then sides to get these two sides congruent? Well, that's wonderful. I'm going to draw this in two dimensions right now just for a sec. I basically have this going on. This is C, P, A, and B. I've got my right angles there. I've got these from the if sides then angles from the three-dimensional aspect of this whole thing, all right, from one triangle to another. And then I've got reflexive. That's a hypotenuse leg right angle situation that we got going on right there. Awesome. So I can get those two triangles congruent, and then I can get the the PA and PB congruent, and then if sides, then angles from there. So let's try and write this thing up. It is quite the involved proof, in my opinion. So let's see what we can do here, and I can make this a little smaller because we're going to need that room. All right. Cool. So I've got step 1, my given. Step 2. Okay. So for step 2, why don't we go right off the bat, we'll say that CP is perpendicular to both PA and PB. And their reason is if a line is perpendicular to the plane, it's perpendicular to the lines in the plane. So line perpendicular to plane, then perpendicular to lines in the plane. And obviously those have to go through the foot, otherwise how can they be perpendicular if they don't even touch? All right, so then I have some right angles, right? So I've got angle CPA and angle CPB are right angles. Cool. And that's definition perpendicular. And since I'm using hypotenuse like right angle, I don't need to say that those are congruent. If you do, it's not wrong. It's just an extra step that's not needed. So I've got also, we said CA is congruent to CB. And that's by if angles, then sides. And so you're looking from one triangle, that triangle CAB, and using the if angles and sides there, and since you're in 3 dimensions, it then goes into those other triangles. Kind of interesting how that works. At least I find it interesting. You guys may not find it interesting, but, you know, I love this stuff. All right. So we got that. Last thing was the reflexive property. CP is congruent to CP. Awesome. So from there, I get my triangles congruent, right, by hypotenuse like right angle. So triangle CPA congruent to triangle CPB by HLR. Okay. Now I know that I can prove PA congruent to PB in order to use if sides then angles, right? In order to use if sides then angles to get my final proof. And I'm again running out of room. Alrighty, so we've got angle, we got PA congruent to PB by CPCTC, and then finally, my proof angle PAB is congruent to angle PBA by if sides then angles. Lovely. That was so much fun. I love this kind of stuff. You know, it's like, hey man, I had trouble with 2-dimensional proofs. Let's throw some 3-dimensional proofs my way, right? Isn't that just fun? Well, really they're the same type of proofs. We're just looking at a 3-dimensional diagram. The only new stuff, the only stuff that's new here is this theorem right here. Step 2, that is the only thing that's actually new. So this is really a reinforcement of those 2-dimensional proofs that you know and love so much.